Have you ever wondered why cakes rise so perfectly in the oven, why bikes left outside start to rust, or how soap magically lifts away dirt from your hands? The answer to all these everyday mysteries is chemistry, a science that's happening all around us, every single moment. Chemistry is the science of matter, what things are made of, their unique properties, and the fascinating ways they can change. It's about understanding the building blocks of everything, from the tiniest speck of dust to the largest mountain. Everything you see, touch, taste, or breathe is made of chemicals, including you. The air you inhale, the water you drink, and even the food you eat are all made up of different combinations of atoms and molecules. When you understand chemistry, you start to see the world on a much deeper level. It explains why salt melts ice on winter sidewalks, how batteries power your favorite devices, and why certain reactions happen the way they do. Chemistry isn't just something that happens in high-tech labs, it's everywhere, from the energy the sun gives us, to the way your body digests lunch, to the colors you see in a sunset. It's the foundation for incredible innovations in medicine, agriculture, new materials, and even the clean water that flows from your faucet. Chemistry helps us solve problems and improve lives. Without chemistry, we wouldn't have the modern conveniences and technology that shape our lives today, from smartphones to safe transportation and advanced healthcare. As we begin our journey into general chemistry, think about how these ideas are woven into your daily routine, influencing everything from the food you eat to the air you breathe. This isn't just about memorizing facts or formulas, it's about discovering a new way to see and understand the world around you, with fresh eyes and curiosity. By the end of this journey, you'll be able to appreciate the elegant dance of atoms and molecules that make up everything you know. So, let's dive in and unlock the secrets of the science of stuff together. Everything, from stars to sand, is made of atoms, the universe's building blocks. Atoms are incredibly tiny, made of even smaller particles: protons, neutrons, and electrons. The nucleus at the center holds protons, positive, and neutrons, neutral, while electrons, negative, zip around outside. The number of protons defines the element. 1 proton is hydrogen, 6 is carbon, 8 is oxygen. Change the proton count, and you change the element. Atoms can have different numbers of neutrons, isotopes, or electrons, ions, but the proton count stays the same for each element. Ions, atoms with extra or missing electrons, are key to many chemical reactions, like forming table salt. These three particles, protons, neutrons, and electrons, are the foundation of all chemistry. Understanding them is your first step to unlocking the secrets of matter. Let's see how they're organized. The periodic table is chemistry's ultimate blueprint, organizing all known elements. Each box shows an element's symbol, name, and atomic number, the number of protons. Elements are arranged in rows, periods, and columns, groups, that reveal patterns in their properties. Elements in the same group share similar behaviors because they have the same number of outer electrons. Metals dominate the left and center, shiny, conductive, and malleable. Nonmetals are on the upper right, often gases or brittle solids. Metalloids, along the dividing line, have mixed properties and are vital in electronics. The table's structure lets us predict how elements will react just by their position. It's not just a list, it's a map to the universe's building blocks. Next, let's see how these atoms connect. Atoms rarely go solo, they bond to form molecules and compounds, creating the incredible diversity of matter we see around us. Without these bonds, the world as we know it simply wouldn't exist. From the air we breathe to the water we drink, everything is made possible by atoms sticking together. Their goal: a full outer shell of electrons, usually 8, the octet rule. Atoms are constantly seeking stability, and achieving a complete outer shell is the key. Noble gases, for example, are already stable, which is why they rarely react with other elements. Atoms achieve this by sharing, giving, or taking electrons, forming 3 main types of bonds. Each type of bond has its own unique way of helping atoms reach stability, and these interactions are at the heart of chemistry. Covalent bonds. Atoms, usually nonmetals, share electrons with each other. This sharing creates strong connections, holding the atoms tightly together. Many of the molecules essential for life, like DNA and proteins, are held together by covalent bonds. Water is a classic example. Oxygen shares electrons with two hydrogens, making everyone stable. This simple arrangement gives water its unique properties, like its ability to dissolve so many substances and support life. Ionic bonds. One atom, usually a metal, gives up electrons to another, typically a non-metal. This transfer creates charged ions that are strongly attracted to each other, forming solid structures. Sodium donates an electron to chlorine, forming table salt. Opposite charges attract. This is why salt forms crystals and dissolves easily in water. Metallic bonds. In metals, electrons flow freely in a sea, making metals conductive and malleable. This electron mobility is what allows metals to conduct electricity and be shaped without breaking. These bonds explain why water is liquid, salt forms crystals, and metals bend without breaking. The way atoms connect determines the behavior of every material around us. The type of bond determines a material's properties: hardness, melting point, conductivity. Whether something is brittle, flexible, or able to carry electricity all comes down to how its atoms are bonded. Chemical bonds are the glue of the material world. They hold everything together, from the tiniest molecules to the strongest structures we build. Next, let's look at the forces between molecules, which add another layer of complexity to the way matter behaves. Beyond strong chemical bonds, molecules interact through weaker forces called intermolecular forces, IMFs. These forces decide if a substance is solid, liquid, or gas at room temperature. Polarity is key. In polar molecules like water, electrons aren't shared equally, creating charged ends. Water's polarity leads to hydrogen bonds, strong IMFs that make water unique. Non-polar molecules like oil don't mix with polar ones, hence, oil and water separate. Soap bridges the gap. Its molecules have a polar head, loves water, and a non-polar tail, loves grease. Soap grabs grease with its tail and water with its head, letting you wash away dirt. IMFs explain why substances mix, separate, or dissolve. They're the reason for everything from rain to clean hands. Now let's see how energy changes matter's state. Matter exists as solids, liquids, gases, and, at extreme energy, plasma. The state depends on particle energy and the strength of intermolecular forces. In solids, particles are tightly packed and vibrate in place. Think ice or rock. Add energy, and particles move more, breaking free into the liquid state, like water flowing. More energy lets particles escape as gas. Steam fills any container. In gases, particles move fast and far apart, with little attraction. Heat a gas enough, and you get plasma, a soup of charged particles found in stars and lightning. Changing states is all about energy and particle interactions. These transitions power everything from weather to cooking. Next, let's see how atoms rearrange in chemical reactions. Chemistry's heart is the chemical reaction, atoms rearranging to form new substances. Bonds in reactants break, new bonds form, and products emerge. No atoms lost or gained. This is the law of conservation of mass. Common reactions: synthesis, building up; decomposition, breaking down; single and double replacement, swapping partners. Rusting iron, decomposing water, and mixing solutions are all examples. Chemists use balanced equations to show reactions, same number of each atom on both sides. Because atoms are tiny, chemists use the mole, a huge number, 6.022 x 1023, to count them. Moles let us measure and mix chemicals accurately. Chemical reactions power everything from batteries to baking. Next, let's explore acids, bases, and the pH scale. Acids and bases are two sides of chemistry's coin, each playing a vital role in the world around us. Acids release hydrogen ions, H+, in water, think lemon juice or vinegar. These substances taste sour and can react with metals, making them easy to recognize in everyday life. Bases, on the other hand, accept hydrogen ions or release hydroxide ions, OHI, like baking soda or soap. Bases often feel slippery to the touch and are found in many cleaning products. When acids and bases mix, they neutralize each other, forming water and salt. This reaction is essential in both nature and industry, helping to balance chemical systems. The pH scale, ranging from 0 to 14, measures how acidic or basic a solution is. A pH of 7 is neutral, below 7 is acidic, and above 7 is basic. Everyday items like coffee, milk, and bleach all have their own place on this scale. Each step on the pH scale represents a tenfold change in acidity or basicity, making small shifts significant. Scientists use pH meters and indicators to measure these changes precisely. Stomach acid is very acidic, with a pH around 1.5, helping us digest food. In contrast, blood must stay near pH 7.4 for our bodies to function properly. Soil, rain, and even your body depend on the right pH. Plants need the correct soil pH to absorb nutrients, and aquatic life relies on balanced water pH to survive. Acid rain, caused by pollution, can harm forests and lakes, disrupting delicate ecosystems and threatening wildlife. Understanding pH helps us manage health, food, and the environment. From cooking to environmental science, pH knowledge is a powerful tool. Acids and bases are everywhere, shaping our world in ways we often overlook, from the food we eat to the air we breathe. Next, let's see how electrons drive chemistry, powering reactions that make life possible. Electrons are the real drivers of chemical reactions. Their movement, shared, lost, or gained, creates bonds and powers reactions. Redox reactions, reduction-oxidation, are all about electron transfer. Oxidation is losing electrons, reduction is gaining them. These paired processes fuel everything from burning wood to running batteries. In batteries, electrons flow from one material to another, creating electricity. Electrons occupy energy levels, shells, and orbitals, shaping how elements react. The outermost electrons, valence electrons, determine bonding and chemical behavior. The periodic table's patterns come from electron arrangements. Mastering electrons unlocks the secrets of chemistry. And that's the electrifying heart of the chemical world.